of the disk, the cool gas. I will focus on the cool gas, so on the millimeter wavelength observations of molecular lines. We'll discuss a little bit molecular abundance. First, some basics of molecular spectroscopy, then molecular abundances, molecular line observations of disks, and what they trace about the kinematics, the turbulence, the mass of the disk. And then I will go to the water, tracing water and the iteration and the link with the solar system. And then I wanted to cover complex molecules, but I doubt that I will be able to do it this morning, and so perhaps I will have a few slides this afternoon on those. I just read the feedback during Phil's talk this morning, so I didn't have much time to distill anything out of them, but there were basically two themes, two requests. One, to hear more on dust traps. You just heard it, okay? I will say a little bit more on observations of this confinement of dust this afternoon when we discuss the asymmetric disks and transition disks and evolution. And some of you wanted more on laboratory experiments of dust and collisions. I will not have time to go into any more details, also because I'm not an expert of these. I would suggest to look either at the PP6 review that we wrote, that includes some discussion of that, but in particular, I mean, the real experts, at least where are those in the laboratory groups, and there is a very good review in the annual reviews of astronomy and astrophysics by Bloom and Wurm that you should look at if you are really interested in the details of the laboratory experiments of dust-dust collision. One thing that I did not say yesterday, and is perhaps relevant, is that most of the dust experiments that have been done so far are actually with bare grains, okay? So they are silicates particles without ice on the surface. And so this might change quite a bit the result of the outcomes of the collisions if you have an ice mantle, okay? And this is difficult to do, and in the laboratory they are trying to start now to do this type of collisions, which is probably very relevant for the growth of dust in the outer disk. Okay, so this is an uncertainty that I forgot to mention yesterday, but it's important. Okay, let's go on the molecules and the gas, the focus of today. And first, I have a few slides that for many of you perhaps will be too simple, but I think it's good to remind what we are exactly discussing. So molecules are a little bit more complicated than single atoms that are already more complicated than hydrogen in spectroscopy. So it's very complicated, the molecular spectroscopy of molecules, and essentially have three types of transition following the standard fact that you can separate the Hamiltonian terms of the molecule in three big energy states, one corresponding to electronic states, so essentially where the electrons in the cloud around the molecule are sitting, essentially. The other, the vibration, stretching, and bending of the position of the atoms. So if you think of a molecule with several, the stretching would be bending, and the vibration of the position of the atom. You can imagine all sorts of possible contortions that basically rearrange the position of the nuclei of the molecule. And then you have the lower energy transitions, which are the rotational transitions. So essentially, you think of a molecule of a rigid rotator, and the mode of rotation is these energy states. So basically, the way it works is that the electronic states are more energetic, so they correspond to higher frequencies. So this is, for example, an example for the CO molecule. So the electronic transitions of the CO molecule you see correspond from the ground state to the first excited state, correspond to a 1500 angstroms, so in the ultraviolet, and so on and so forth. Okay, so these are high energy states. Then inside each of the electronic state, you have the vibrational states. So the two carbon and oxygen, this is easy, so it's a bidimensional molecule, it's a monodimensional molecule, biatomic molecule, so the simple vibration is the distance between the two atoms, the two nuclei, sorry, that oscillates, okay? And so this is the vibrational states that, as you see, have lower energy and correspond to the ground, from the ground to the first excited state. The transition is around 4 microns, so in the mid-infrared. And from the second to the second excited to the zero state correspond to 2.35, which is the familiar CO raw vibrational ladder that you observe in the cool atmosphere of stars, for example, at 2.5 microns. Okay, and if you look again inside these vibrationally excited states, you have all the rotational states, so the state of rotation of the molecule. No, this is low molecules rotating, and you see that basically are described by the angular momentum number, and you see that from the ground to the first excited state, the transition corresponds to 2.6 millimeter in wavelength, and these are the transitions that we observe in the millimeter and in the sub-millimeter. Okay, and they correspond to well, I think I have in the next graph the temperature at which they correspond. But that basically, this is the 3 millimeter, this is 1 millimeter, and this is the 850 micron transition. Okay, that's a simple molecule, and the rotational lines, if you want to compute yourself at home, instead of looking into the database where they are tabulated, you can compute them following this formula. The key thing is that the rotational constant here in front depends on the reduced mass of the molecule. So the more massive the molecule it is, the lower energy are these transitions, okay? So this already tells you that if you want to go to light molecules, which obviously are the most abundant in the interstellar space, they will go to higher and higher frequencies, okay? Obviously, this is an approximation because as the molecule rotates, the separation between the atoms increases, and so there are correction terms. So this is a simple thing, okay? The selection rules typically for this type of transitions are that you basically have spontaneous transitions only for delta J equals 1. So you move through adjacent levels in the ladder. And the other problem is that you need to have a permanent dipole moment in order to have these allowed transitions. This means that the molecule that we would like to observe, which is obviously the molecular hydrogen, which is the most abundant molecule, does not have these transitions, okay? So molecular hydrogen cannot have these low temperature, low frequency transitions. Symmetric molecules can only have quadrupole transitions, which are obviously harder to excite and corresponds to higher frequencies. And in fact, the first transition that is observable of molecular hydrogen is the one that falls into the infrared. Okay. Similarly, carbon-2, oxygen-2, and so on and so forth do not have permanent dipole moment, so they are not easily observable. Okay. Okay. Again, this I said it already. All of it. This is a sample of simple diatomic molecule, reduced mass total mass 7, compared to H2, which is why is 0.5. There is something wrong there. Anyways, as I said, these are the spacing of the CO ladder, and basically this is the one of molecular hydrogen that I just told you before. So the first exciting line, the first line cannot be the 1 to 0, has to be the quadruple line, so 2 to 0, and is a 28 micron. And to excite it, you need to go to fairly high energies. Okay. If you have a more complex molecule, so for example, you have a molecule that is a symmetric top, which is the next simplification. So a molecule that has two two moment of inertia along two of the axes. Well, they have one preferred symmetry axis, so they have one moment of inertia through that axis, and then symmetry on the other axis. These molecules typically are very good tracers of temperature because they thermalize very nicely, and they are described. They're thermalized very nicely on the ladders of the same projection of the angular momentum to the axis of symmetry, okay? They are typically described by two quantum numbers, the transitions. One that is obviously the angular momentum, and the other is the projection of the angular momentum of the axis of symmetry, essentially, okay? And these molecules all have this type of structure of levels, and they basically tend to thermalize very easily along these ladders, okay? So measuring the ratio of these lines is usually a good tracer of temperature. In the case of ammonia in particular, you see that the states, the ground states are, not the ground states, the states of the molecule are all double. They are double because it matters whether the nitrogen is above or below, considering the spin of the nitrogen is above or below the plane of the hydrogens, okay? The energy is slightly different, and the transition between these two states is called an inversion transition. Okay. If you have a molecule that has no axis of symmetry, the rotational spectrum is much more complicated. And so here you have, for example, the case of water, which is which you need to describe by the total angular momentum and the projection of the angular momentum on two of the three axes, essentially. Okay. In addition, water has another complication. Since it has two hydrogens, it matters whether the spin of the true hydrogen is parallel or anti-parallel. And for reasons that escape my comprehension, para means when they are anti-parallel, and ortho means when they are parallel, actually, okay? Whatever the reason is. And in interstellar conditions, the transitions between these two states are very difficult, okay? So normally, you have water that, if you form water in a para version, then it stays in the para version, okay? All right. Having said that, what are the abundances of the various molecules, and which molecules should you observe if you want in the interstellar medium? This is a collection of measurements of abundance of the various molecules with respect to hydrogen, to molecular hydrogen, total hydrogen, let's say, but in molecular clouds is essentially molecular hydrogen. And this is a compilation that you find in the book Tools of Radio Astronomy, by the way. I forgot to put the reference. And what you see is that typically CO, that is the molecules that is most observed in the interstellar medium, has an abundance with respect to hydrogen in a variety of environments. So Taurus cloud, protostar, Orion diffuse, the Orion ridge, the Orion hot core, the late type star, okay? In a variety of environment, but not in the late type star, has an abundance of the order of 10 to the minus 4 compared to molecular hydrogen. So if you want to trace molecular gas with the total mass of the molecular gas with the CO line, okay, you need to apply exactly as you do with the dust. You need to apply correction factor because with CO you only observe a fraction of the molecular gas. And instead of applying a factor which is 100 for the dust, you apply a factor which is 10,000 for the gas, okay? The other important molecules, well, all the other molecules are much less abundant. So if you take, for example, even NH3, which is a typical, that I showed the spectrum before, it has an abundance which is of the 2 orders of magnitude lower than the abundance of carbon monoxide, okay, typically. And you see the range of abundances in the various type of regions. If you go to complex molecules, obviously, they are even less abundant. That's sensible. If you go to SIO, it has an abundance that is hugely different in different regions. And that's because SiO is actually contains a silicon, no? And silicon and oxygen, and these molecules tend to go in the solid state. So normally you don't observe it unless you destroy the dust grains. And so to observe SiO, essentially you have to destroy the dust grains. So for example, or form the dust grains, no? So for example, you see it abundant in late type stars because you form silicon and oxygen, and in these stars, in the interior of these stars, in the wind of these stars, these two combine, and so you have a phase in which these two are in the molecular phase before they condensate into the dust grains, okay? And so that's why here is abundant. In supernovae is abundant, SiO. So supernova 1997A, there are observations from ALMA of SiO in the gas phase. But as you go into the molecular clouds, especially in cold molecular clouds, you see that there are upper limits of the gas phase abundance. That's because they are in the dust grains. And you basically see, for example, in the hot cores, because it's connected to the destruction of grains. Okay, the last thing that I want to say here, I want to point out to this thing here, okay? The abundance of water in IRC 10216, okay? So it's not CO that is the most abundant molecule, it's water the most abundant molecule. Why? Well, there are two points here. Water and CO compete for carbon, let's say this different way, carbon and hydrogen compete for oxygen normally in the interstellar medium conditions. So what happens normally is that all oxygen is locked into CO, and then what is available on top of what has been locked into CO goes into water. So that's the normal situation, unless you have an atmosphere that is poor in carbon, like it was a gas that is not as abundant in carbon, and so you have an enhancement of water over carbon monoxide. The other thing that you notice is that there are not abundance measurements of water in all the other cold clouds. That's because, for two reasons. One reason is that water is difficult to observe. There are now observations of water abundances. And the second reason is that water, like water has a condensation temperature, as we were saying before, which is higher than CO. So it's much easier to condensate water onto the mantles of dust grains than CO. And so there are a lot of situations in molecular clouds in which the temperature and pressure are such that CO is in the gas phase, but water is in the solid state. Okay, so that's why water is not as abundant and is not nice tracer as CO. The reason why, sorry, I didn't conclude, I think, the sentence. The reason why H2O is difficult to observe from the ground is obviously that you have water in the atmosphere with a relatively high optical depth for our good health. So it's difficult to observe water from the ground, unless you look at isotopes and rarer things which are difficult to observe. Okay. So this whole discussion was to basically tell you why we are using CO as the main tracer of gas, for example, in disks so far, and I will discuss mostly CO, and then I'll go to the other molecules at some point. Okay, molecular gas in disks. So disk has to be gas has to be very abundant in disks, and this you know from many reasons. Well, the first reason is that disks are flared, and the dust alone cannot flare. So basically, this is the easy thing to say that gas has to dominate in disks. Okay. There are direct measurements of the gas from the cold phase, which is what I will discuss. That's why it's in red. And there is also direct measurements of warm gas in this tracer in the very inner disk, okay, where the disk is hot, and so you can basically excite the quadruple transitions of molecular hydrogen, or you have the vibrational transitions of CO, or you have the infrared transitions of the vibrational transitions of water. We also measure it indirectly through the accretion rates and the winds, so the fact that there is enough material to have the accretion. If you look at where the gas is and how you can probe it and what are the processes that are connected, this nice cartoon from a review by Evin van Dishoek clearly explains this. The gas disk is on this side and the dust disk is on the other side, okay? So basically, the disk, as we have seen, has a radial and vertical temperature structure, so is cold in the outer midplane and hot in the surface and in the inner region. So you already expect, obviously, to have atomic or high excitation molecular gas in the atmosphere of the disk and close to the central star. Then you have what is normally referred to a warm molecular layer, which contains the molecules, the simple molecules in a gas phase, okay? And then when you go to the cold midplane, most of these simple molecules condensate, so you don't see them anymore in the gas phase, and you may have some particular molecules like the deuterated molecules in low abundance, or molecules that are hard to condensate. Okay, so this obviously creates a little bit of a complication. One has to be careful in what is observing and how is interpreting the molecular gas observations. So this is how a disk looks like if you observe in one of these simple molecules. These are CO observation, carbon monoxide observations in transition 3 to 2 from ALMA. This is the total intensity of a disk that I think I've shown yesterday in the continuum. It is this disk here around a 1.5 solar mass star, roughly speaking. And this is the first moment in color of the CO emission, showing essentially the mean velocity in the various positions of the emission. So you see that there is the velocity gradient, which is obviously the Keplerian rotation pattern. And in the contour, you see the emission from the millimeter continuum, so the dust grains. And immediately from this picture, qualitatively, and then we will show it more quantitatively afterwards, qualitatively you see that dust, at least the dust that we observe in the millimeter, and the molecular gas does not appear to be well mixed, okay? So there appears to be a separation between the gas and the dust. This is another molecule, essentially, same disk, and basically what is shown here is one of these infamous radio astronomy diagram. Is a velocity position diagram across the main axis of the disk, which shows essentially the Keplerian pattern that you see here. So here is the position of the star, and this is the velocity of the star. As you go close to the star, you have high velocities in the gas. And as you go away from the position of the star, obviously the velocity goes down as expected from Keplerian rotation, roughly speaking. Okay, and then we will see the detail later on, but the main profile is essentially the Keplerian decreasing profile. If you want to model simply a disk like this one, this is the simple way of doing it. The simple way of doing it is assuming that you have a hot layer that is emitting the gas, okay, hot thin layer, and then basically your emission is just the integral at each position is the integral along the line of sight, because you have to take into account the optical depth of the source function time the opacity there. Okay, and you see here that one can make these simple approximations using essentially the partition function for the molecule at the temperature that you have, and you can derive essentially from the observation the profile of the temperature, the profile of the emission of the gas. And if you do this in a very simple way, this is what you expect in terms of spectrum. So you expect a spectrum that is double peaked normally, okay, for a slightly inclined disk. And if you look at the image that you expect at the various velocities, if you look at the systemic velocity, you expect to see the gas that has a zero component with respect to your line of sight. So the star is in the middle, you expect to see this butterfly shape. As you move away from the central velocity in the line, you see one side of the disk, obviously, the other side is symmetric on the other side, and you see this butterfly shape which goes in the outer disk for low velocity and come back in the inner disk for the high velocity, obviously to take into account the Keplerian motion. So these simple models account very well for the emission that you see. So I mean, these are parametric models, no? So you are not understanding the big physics that is behind the molecular emission. You are just trying to extract some basic parameters, that is the typical temperature of the gas that is emitting, and the rough kinematics of this gas, okay? So one should not overinterpret these models, but are interesting to get these simple parameters out of the disk. And basically, this is the example on the same object again, different observations, but the same object. This is the model, and this is the observation. So this is the systemic velocity, and this is the fit and the residual. So you see that is fairly well representative of the observations, okay? So with this simple thing, you can derive a temperature for the molecular layer, and you find that it has a temperature that is intermediate between the midplane and the atmosphere, and depending on the molecule that you look at, you probe different layers in the disk, and so you see essentially a variation of this temperature. Okay, and all of this is more or less consistent with what you expect to see. Okay, so you can derive essentially the kinematics of the disk, rough physical properties like temperature, abundance, and gas-to-gas ratio, very roughly, okay? And you can try to look at the chemical processes, as we will see before. Before we go into more details, I want to show in a more quantitative way the difference between the molecular gas and the dust in the disk that I showed before. So this is the dust continuum and the molecular gas image, and this one is a brightness profile, so it's very just the observed profile, okay? And you see that in the dust you have the decrease in this log-log scale. Essentially this is the power law part, as we discussed yesterday, and then there is the exponential cutoff, and basically you see that the dusty disk for millimeter-sized grains is of the order of 200 AU in radius, while if you look at the CO, the profile is much broader. It still has a similar shape, although there is a small excess here, but it has a similar shape, but the cutoff is much larger radii, and you end up to 1000 AU in radius, okay? So this is in fact consistent with the expectation from the viscous spreading of the gas with time, and the concurrent migration of the large grains toward the center of the disk. Okay? What is not shown here is obviously that the small grains, so the submicron particles, are still well mixed with the gas. So the submicron particles are connected with the gas, and they extend to larger and larger radii. In fact, if you look at scattered light images of these disks, they look much larger than the millimeter image. So that's because the small particles in the outer disk provides the scattering. Okay. In addition, if you have enough sensitivity like ALMA, you can hope to detect also the wind, and this is one of the few examples of a disk wind, still the same object. The CO disk this time is the contours, and in colors here you have the low level, high velocity, much higher velocity emission from the CO, which you see is coming from the disk, and actually is, if you look at the kinematics, which is this one, you see that this arm here, if you want, is toward red velocities, while this arm here is toward blue-green velocities, consistent with the fact that this wind has been launched from the disk and is keeping the same kinematical structure, essentially. These, I think, will be very interesting in the future to measure direct, because outflows, molecular outflows, obviously from young protostars, so from class zeros and even from class 1 systems, are very well known and have been studied quite a bit, but from a classical disk phase, the role of the outflows and how much material and angular momentum you are extracting from the disk using outflows is still to be constrained observationally. So this type of observations are important in the future when they will become more easy to do to some extent with ALMA. Okay. The final thing that I want to say is that if you want to do a more detailed modeling, I mean, if you have good observations like the ALMA ones, doing the simple modeling that I just showed, the thin slab, is not enough, okay? And that's because at the angular resolution and sensitivity of ALMA, you start to see the fact that the disk is not, the molecular disk is not a thin layer, but has a structure that is a warm layer, essentially. So this is a representation of where the CO is coming from in this disk. The dotted line are essentially densities, total gas densities in the model. And this gray area is the region where CO is not photodissociated, because if you go too high in the atmosphere, the UV photons from the star dissociate the molecule, so and the temperature essentially dissociate the molecule, so you lose it. If you go too deeply into the disk, then the temperature is too low, and the CO condensates. Okay, so as I said before, the CO is coming from this layer, obviously, from this layer, and from the symmetric layer down there, obviously. Okay, so when you observe this disk, you basically, at any given velocity channels, you see the top layer and the bottom layer, okay, of the disk. And in fact, you have to do some more complicated models. And if you do a model that includes this structure, essentially, this is just a model of 2 layers, okay, 2 layers with an angle between the two. And you see that the angle that you have to apply, these are the 2 layers, the red and the blue, okay? So the red layer is approximately at 10 to 15 degrees above the midplane, and the blue layer is approximately 10 to 15 degrees below the midplane, okay? As you expect from this modeling. So you need to be, as the observations get better, as usual, you need to be a little bit more careful in the way you do the modeling and the way you extract the parameters from the data. Okay, I think I want to stop here for 5 minutes before going to the other topics. And my suggestions for thinking are, why is CO our prime probe of gas and not something else? I partly already said this. And why should CO to HCO be a better probe of the total mass of the disk if the correction factor is 2 orders of magnitude larger than the dust? This was one of the questions from some of you in the feedback. Why do we use dust as a tracer of mass if the correction factor is actually smaller than the one that you use on CO? Naively, you would expect that, you know, if I get wrong CO, then given the correction factor is 10,000, the mass will be more wrong, the mass that I get, okay? And what are the difficulties in using gas as a tracer of anything in general?